Hello again, folks. Today we're going to do the last section for the semester, which is discussing 11.6, something called Conditional Probability. Now, because it has some similarity to the things that I had already talked about, I figured what I would do is start with the diagram from last time, go through the intricacies of it for a moment, and then show you what is different about it. Okay? So here's the first thing. Do remember, right, that in terms of compound probability, there are basically two types, the or and the and type. So if you could spot those two words, you're already ahead of the game, because then you could just define it as either mutually exclusive or not mutually exclusive. All right, in the or case, and dependent or independent in the and case. Now, as far as mutually exclusive is concerned, that means that two events cannot occur simultaneously. Do remember that. Whereas, if you have a situation where the events are not mutually exclusive, that means, to sound somewhat contradictory, that they can occur simultaneously. We had discussed some examples of each of those last time. In terms of dependent and independent events, when events are dependent, that means, I'll use red here to make it a little bit more distinct, that the second event is affected by the first. And usually the subtle indication that you have this situation is the phrase without replacement, which I'm just going to abbreviate as W/O, without, right? Replacement. You see that in a sentence, in context, gravitate towards this formula. Right? And alternatively, I'm going to make this, just for the sake of symmetry here, blue as well. In the case of independent events, which I'm trying to save some space here, that's why I've sort of locked it into this little block. All right. These events, one event has no bearing on the other. They are truly independent of one another. It's like playing two different games, like a die roll in the first game and a card draw in the second game. All right, one cannot affect the other. They're two different things. Okay, hopefully that is legible. Looks like it is. Okay. All right, and there are formulas that we had from last time. These are going to kind of be revisited in a moment, but let me just distinguish these now from yet a third category, if you will. When we're talking about and in this context of dependent or independent, I'm going to add one phrase to this, all right? It's really when you see the phrase and then that is a good indicator from this point forward that you would say, yeah, it's probably dependent or independent events, and therefore those formulas respectively. These can be considered consecutive events. Because one follows the other in time, right? That's really what's going to be necessary to grasp in order to distinguish it from this third category. So now we have this, right? We have basically the consecutive events versus conditional probability. All right. And as far as time is concerned, in the case of conditional probability, a time relationship doesn't actually matter. And in the case of consecutive events, it is important because one thing follows the other. But in the case of conditional probability, the time relationship does not matter, right? And consequently, it'll have its own unique formula. All right. So that is to summarize what is old with what is new. Now, let me give you another diagram to help distinguish this a little bit further. Just erase nicely today. Let's distinguish these things a bit more, especially in the context of English, because English can be inherently confusing and problematic. Okay, so in terms of probability, think about it this way. We have the two consecutive events and then we have the conditional probability. For the sake of contrast, all right, let's make this distinction. If this is going to write clearly. Let's discuss context. Again, both of these involve the word "and" somehow. Well, you will notice that they both involve the word "and." Consecutive events, dependent and independent events for sure, all right, but conditional probability as well. Okay. Now here's the context, the contextual difference between these two things. When you're dealing with consecutive events, all right, the word "and" in this context, whether they use the word or not, means this and then. Okay. So affiliate, even if it's just written, sloppily or lazily, perhaps that's a word. Just one word "and." Think of it as being "and then." All right, meaning two things. One thing follows another. They're consecutive. All right. This is when something occurs and then something else. In this situation, the context of "and" will be a bit different, right? So associate "and" in this context with intersection. and this is basically when something is two things. Is both conditions, hence conditional. Again, English, as I often say, I complain about it, and I'm saying this as a person who speaks English purely, right? I wish I were more sophisticated than that, but English, when it comes to teaching math, gets you in trouble, all right? Why? Because the words are ambiguous, right? We have, lots of different meanings assigned to the same word, so it is a good idea to distinguish things, what the context is, all right? So intersection, as far as intersection is concerned, let's just say you don't remember, right? When we were talking about sets, right? Here's a little thought cloud. Remember, sets are something you could summarize with a Venn diagram. Set A and set B. The intersection of two sets would have been the overlapping area. So I'm just going to designate that with a little shading here. The overlap. All right. The overlapping area is the intersection. And there's a symbol that we have for that, remember? All right. The symbol for intersection is that sort of upside down U. It's let's just call it a horseshoe, like this. So in the formula, right, for the sake of clarity, believe it or not, I think we're going to favor using this symbol, right? Just not to confuse it with the formulas that we have established for consecutive events, okay? Dependent and independent probabilities, okay? In the textbook or elsewhere in other textbooks, very often they will not make that distinction, and they really should, because this is very specific, right? So look for that symbol, the upside down U. Okay. Now, as far as the formula is concerned, let me show you sort of two different versions of the same formula, all right? And then I'm going to basically emphasize the last one, because the last one I think is the best one. I really should leave it to you to decide, but all right, I want you to see sort of the evolution in thought here. Let's label this as such. The actual formula that you would utilize. Okay. In some textbooks, right, they will sort of, for the sake of consistency, they'll stick with the symbols A and B to say, okay, there's two different things going on here. So you might see this elsewhere. Okay. Now it is kind of implied when you're looking at this incarnation of the conditional probability formula to go, oh, A and B are alphabetical, so A is the first thing, and it is. It's the first condition, right? B is the second condition. Now, perhaps somewhat ironically, in the formula, you will see that B is written in the front, right? That means that B is affected by A. Right? So it has some kind of similarity already to dependent, all right, probability. You would read this as B given A condition. The condition of B given that A has occurred, or that A is part of the situation. The problem with that, I feel, is that when you get to this half of the formula, they don't make the distinction between consecutive events and really what are conditional events. We're really talking about the same item, all right? But an item that has two qualities, all right, at the same time. So, although you will see this here, right, and they will not draw any other distinction, just realize that the "and" written here is referring to an intersection, right, rather than consecutive events sometimes. Okay, so be careful of that, right? Conditions that are shared within the same item or element. Okay, now here is a slightly tweaked version of this formula, right? In which, and I'll label it as such, slightly better, I feel personally. Which they call the probability of event 2 and event 1. And so instead of using letters A and B, even though it is implied, naturally, that they are one thing following the other somehow, right? Not really, if we're just talking about an intersection, but they're talking about two different unique things. Okay? The formula changes a little bit on this side here. Take a look at this. You'll see this instead. Now let me say up front, aside from the obvious, that we're opting for, in this case, subscripts, all right, to make a distinction between two different characteristics. Instead of using A and B, we're using E subscript 2, E subscript 1. This is the first, this is the second. Yes, ironically, the second is written in the front, right? Why? Because again, you would read this as the probability of event 2 given event 1. Now notice this other distinction to complete this thought, all right? These are not probabilities per se, all right? If you use this formula or use this formula, you're going to get a probability because of the way that the math works out, all right? But you notice that this is presented in a slightly different phrasing, all right? This is the probability, which puts the burden on you, the user of the formula, to go, okay, I have to figure out what the total is to make a denominator. That is, I'm making a fraction here, and I'm making a fraction here. In this case, they're kind of eliminating unnecessary steps in theory, so that you're not finding probability so much as you're finding parts of a probability, and then combining them into one fraction so that the end result is a probability. I'm going to give you an example in a little bit, and you'll see the intricacies of what I'm saying, right? But just make that distinction. You're looking for the number of outcomes favorable to event 1 and event 2. And down here, the number of outcomes favorable to event 1 only, right? Because of the mechanics of the intricate work of what would be involved in this calculation, there's a cancellation effect that you don't actually have to worry about. That's why they've simplified the formula from what you might see in another textbook to just this. Even nonetheless, it can be simplified a little bit further. Right? Because again, what have they done? They've still kind of committed this sin. They have not made the distinction between consecutive events and what is potentially an intersection. And that is really the context that I would use this. So, one more step, and then I'm going to say, remember this formula, all right, instead. It is just the same thing written 3 different ways, and this is the last way. And it is the best way, I feel. Not to corrupt your opinion. Yes, to corrupt your opinion, but with good intentions, I swear. So the probability of E2 given E1 is equal to, again, the number because it's less complicated, but event 1 intersecting event 2. Over event 1. Right. I feel, at least insofar as the problems you are inclined to see, all right, in this section, and then I have to show you, right, that this is the best incarnation of the conditional probability formula, right, because it makes this distinction, right, that this is, we're talking about the same thing, the same item, the same element, the same person or object, but it has 2 conditions. It's not like it's one thing and then another thing that is independent of it, right? And I'm not going to use the word and, right? If I could avoid it. Even though it technically would be legally correct, it's confusing, right? So use this intersection symbol, right? And realize we're looking for something that is simultaneously both conditions. Terrible way to write the word, but you just look at that. It looks like it died. I had so much to live for. It jumped off the cliff simultaneously. Okay. All right. Anyhow, still read it as such. The probability of, that is what the P is, event 2 given event 1 is equal to the number of outcomes favorable to the intersection of E1 and E2. All right, divided by the number of outcomes favorable to event 1 only, all right? And it's always event 1. Now, insofar, and you'll see this in the word problems I have, how you decide, right, which is event 1 and which is event 2, because it does matter. You're going to make one of them a denominator, okay? There's a trick you can pull here, right? So, the door's locked. That's mad. Oh, I'm sorry. Shut up!
Bye forever. Love you.
I love you too. It's my sister. Alright, let's see. What was I? Refocus here. Let me erase some of this. Right, and sort of give you a strategy for deciding which is event 1, which is event 2, because it does matter. Okay. You'd end up dividing by a different number if you're not careful. sort of separate myself out here. Make sure I wrote that. That looks like it's good. Okay. When you're trying to decide events, write this. This is a bit faint. I could kind of see it. Is this better? Vaguely. Option 3 here. No, it's even worse. Good grief. Okay. And that's a brain marker too. Yeah, I'll just go with this. When trying to decide events, I would do this. Look for this phrase in the sentence. There'll be the word given, usually a comma here at this point, and then something will follow it. That thing that follows it, whatever is written after the word given, right, usually is event 1, right? It is a little bit, it is somewhat ironic, right? Because you think of, well, the thing that is the most important, shouldn't that be in the front of the sentence, not in English, okay? So in theory, the first characteristic of something may be written at the end, all right? So look for the word given, all right, and it's usually written immediately after it. That's usually what E1 is. Failing that is another strategy that is a little bit more complicated, all right, but it might come in handy, which is this. The most specific characteristic make that E2. Alright, so like if you have two things given to you, you know, humans, and then you could say Eskimos. Eskimos is more specific of a type of human, right? Alright, then you would make that E2, right? If you're talking about, that's another stupid example, cars, alright? And then you're talking about, you know, a Toyota, all right? A Toyota is a more specific type of car, all right? So make that E2, okay? All right, finally, some examples. We'll work this in. Try not to erase this because I'm going to end up needing it for the sake of illustration. It's very windy out today. There's something like the light hanging on my stoop is, I think, like rocking and banging on something, or a tree limb. I'm going to try to sort of write this really quickly. I hope I'm electing the correct marker. All right, let's calculate as an example. It's a bit faint. the probability, this is not much better. Red, don't fail me now. The probability of selecting a card at random that is black. Oh, that is a club rather. Given it is black. And the two key characteristics here are club and black. Now again, it was a bit of a dodo. I'm going to go dig up my cards and then just show you an example of this, because you should never assume that a person has ever seen these things. I'll pull out the fancier one. Here is a deck of playing cards. I think I got these at Barnes & Noble at one point. And let me take out the things that are unnecessary here. It's a very elegant looking joker riding a bicycle. Not necessary. If you take out the jokers, it's just 52 cards. So I'll lose those, put those there. Alright. Now, here's an example of a card that is a club, of course. Right? Notice the color is black as well. Right? There are famously two different suits of black cards. Spades is an example, right? This symbol, and clubs. And two examples of red cards, right? Hearts. That's so sad. I'm gonna have to pick that up now. And diamonds, of course. These are the symbols that we're talking about, otherwise known as suits, all right? I'm wearing this suit today, the hearts, right? Imagine that, you wore hearts, motif, That'd be kind of cool, a little weird, but interesting. Anyhow, these are your basic options in terms of suit. The word suit itself is referring to a color and a design. Okay, now what did I drop? Oh, wow, they really went. What the hell? Why don't I do the smart thing? Not leave them where they fell. Bear with me. I know the special effects are very poor on this program. The hair, cobwebs. And they're so slippery too on top of it. I'll be back. Just try not to lose everything. And I have to probably count these later. Make sure that I didn't lose anything. Because I kind of feel like I did. There's a crevice in the floor here. Just went to the pile and it's never coming back. Alright, anyway, I'm not going to waste time. Got cobwebs. Spiders like to play cards too. Here's a deck of 52 cards because it's a regular poker deck. You've seen the suits and the symbols that correlate. Now, let me put these in a place where they're not going to get in trouble, presumably. Here. Let's answer this question. Let's calculate the probability of selecting a card that is a club, given it is black. Right? This is how we will decide which is E1 and which is E2. Now again, for the most part, at least what I've seen, right, what is E1 is usually part of the phrase that follows the word given. So black is E1. Right? That would therefore force the situation of being a club to be E2. And that conforms to my alternative way of looking at it, which is the most specific characteristic is E2. It's more specific to be a club than it is to be black, because black cards can be clubs or spades. Right? It's more general, right? This is more specific. So if I were going to modify the formula, right, to match the unique example, right, let me input those sort of abbreviations where they would be. Right? In place of E2, since that is written in front here, I'm just going to put C for club. And in place of E1, I'm going to put B for black. So that means that this is B intersect C. Right? And down here we just want B. Now, if we were again to translate the symbols to grammatical English, right? This is the number of outcomes. This is flexing a little too much. That's visible. Favorable to the intersection of black cards and clubs. All right. It's kind of asking you to do some steps in your head, which I hate, but we'll do it anyway. Down here, this is the number of outcomes favorable to black only. And you can think of this as naturally being a total. Basically, this is asking what is the total number of black cards. Right. That's of the two things to deal with, probably the denominator is easier. So, right. In place of this set of symbols here, the sequence of letters, and argument B. Right? Think about in the case of a deck of 52 playing cards, regular standard deck, not a pinochle or anything like that, or an Uno deck. You know, how many cards are black? Right? Just the number. It would basically be comprise or it would account for half of the deck. So if half of the deck is 52 in general, pardon me, if the whole deck is 52, it's half of 52. 26. Okay. Now, as far as the intersection of black cards and cards that are clubs, right? That's really just saying, what is the number of clubs, right? Because in fact, all cards that are clubs are also black, and we only are interested in the clubs. Right? And the reverse could not be said. Not all cards that are black are clubs, but all clubs are indeed black. I hate talking like that, but that's really what's going on here. It is definitely true one way that you say it, and not necessarily true the opposite way that you say it. All right, so we're asking basically for the number of clubs. Why? Because that is the intersection. A card that is characteristically black and simultaneously a club. Of the 26, how many are clubs? All right, and bear in mind that half of 26 is the answer. What's half of 26? 13. Okay. So, if you have this fraction then, you just basically solve this as being 13 out of 26. Notice that it is first of all, it is a fraction, right? 13 out of 26. The fraction can be simplified, and I would attempt to, all right? Sometimes it's not so obvious. If you happen to have a scientific calculator and you enter something in the style of a fraction, there is a button that looks like this, A, B, C, all right? If you press this button and then type 13, pardon me, if you type 13 and then press this button and then type 26, it'll spit it out as the fraction in simplest form, right? It just so happens, and I kind of did the math mentally as well, that this is half of this. So this is what it would reduce to. It's really more concise. It's simplified to say that it is 1/2, right? Which in terms of a percentage is of course 50%. So 13/26 is 1/2, which is really 50%. What is the probability of selecting a card that is a club given it is black? I mean, that is for certain. That means that it's a 50% probability, right? Which is pretty good. It's, you know, it either is or it isn't, right? All right. Now, I don't know if I should take the time to do this, but maybe I'll do this once. You know what the answer is. The answer is 1/2, right? If you choose to go the other route, which is to use the probability formula that has just the word probability in it rather than number, I just want to show you what, you already know what the answer is, that it's 50%, but I want you to see why they work out to be the same thing. There is a little bit of arithmetic that you're familiar with, all right, that is going to correct anything that is needing correcting. Here is the alternative form of this that will produce the same result. This is something that you might see in another textbook. The probability of B given A is equal to the probability of A and B over the probability of A only. How do we decide which is B and which is A? Again, what follows the word given is usually what is A, right? Barring some weird sort of English phraseology. So, all right, that's still going to be black. And this is another reason why I'm mentioning it to you as well. When you're translating something from a generic formula into the unique problem, all right, beware that there are sometimes they share some similar letters, and this is a perfect example of that, but they have different jobs, meaning that they go to different places in the formula. So be careful, all right, where you're inserting your abbreviations. If we're deciding that black represents E1, that's the same as saying black represents A. That means that black is actually here. It's not referring to it as the second characteristic, which is the job of B here. It's saying that this is the first characteristic, the more general, the less specific, all right? Which means that it would be here and here in this incarnation of the formula. Simultaneously, if the second characteristic is the more specific type, the clubs again in this example, then that is what would be B in the formula. That's its job. It's filling in the second characteristic. So it was B to begin with. I shouldn't erase that. This is how you would tweak the formula, right? That means that C would go here. It is confusing, it is annoying, right? But I'm mentioning it so that you don't make the same dodo mistakes that I tend to make, all right? Which is you gotta be extra careful, all right? When you're filling in your variables, all right? Decide what their job is. Decide what the position in the formula represents, okay? So, yes, it's unfortunate that they share this letter in common as a descriptor, all right? As an identifying symbol, all right? But this is what it would translate to. B would be here, C would be here. This is still E2 and E1, which is why I like that formula better. Right? Because the subscripts make it a little bit more distinct, right? Even if they're a nuisance. Anyhow, what is also different here is the way that this is written. This is calculating a probability, all right? And a probability, rather than merely a number, is a fraction. To begin with, there'll be a fraction sitting above the line here, and a second fraction above the line, below the line here. So, what's the probability of getting a black card out of a deck of 52? It would be this. It would be 26 out of 52 cards. Right? You could reduce the fraction if you want. It would end up being half is what it would be. This would simplify to a half. Right? Then there's this. The probability, and this is understood still as being an intersection. What's the probability of drawing a card that is both black and a club? All right? It would be 13 out of 26. 13 out of 52. Now, there might be one advantage to not simplifying, and you'll see in a moment why. Anyhow, if you're writing this as a probability, it has to be in the style of a fraction, above the line, or a decimal, technically, I guess. All right? Not a percent, not yet. All right? So it would be, there are 13 cards that are simultaneously both black and a club out of 52 total. What's the probability of getting a black card? Exactly half of the deck, which is 26 out of 52. Now, here's really why I'm talking about this. If you were to try to mechanically straighten out the arithmetic going on here, right? Notice that it is a fraction sitting on top of a fraction. This is referred to as a compound fraction, right? And if I were to take it from something that is more or less stacked to stretching it out sort of horizontally, this is how it would translate. It would be 13 over 52 divided by, is this line, 26 over 52. Right? And then you would have to employ old techniques, right? When you are dividing fractions, as in this case you would be technically, the procedure to do this is to keep change flip, which is to keep the first fraction arranged as you see it, change the operation, perhaps ironically, to multiplication, and then compensate by using the reciprocal here, which is just this fraction flipped upside down. So this becomes 52 over 26. Now, again, other sort of shortcuts here is that, and if I resisted the temptation to reduce this to a half, this would be where it is practical. You can cross simplify the 52s, all right? Because they're a common factor. They have a common factor. It's weird to say this, but they're both made of the GCF 52. So you can simplify them like so. 52 divided by itself is 1, 52 divided by itself is 1. Right? You could, if you wanted to, at the same time simplify the 13 and the 26, but let's say that you didn't. All right? Then it would be 13 times 1, which would be 13, and 1 times 26, and you'd have the same fraction that we had before, which is 13 out of 26, which is really a half, which is really 50%. All right? Again, the reason that I'm bothering you about this at all is because I want you to realize that whether you have this version of the formula or not, they represent the same thing. It's just that this has sort of a little bit more obvious work involved, because when you form a probability, it is in the style of a fraction, whereas in the other incarnation of this formula, some of the work is going on in your head, all right? Because of the way that it's phrased, number of events, all right? Number of outcomes favorable to the events, all right? You're sort of skipping having to do this work, all right, of keep, change, flip, all right? I think the formula with the intersection symbol and the subscripts E1 and E2 is better, all right? But if you need to, if it makes more sense to you, use this formula. Because it's just the probability divided by a probability. Here's another example. Okay. the probability of getting an A at random for a class, all right, given that you get a grade higher than D. Now again, this is kind of nebulous, so let's approach it with strategy. First of all, write the formula. All right, what's the formula again? Let's do this. The probability of event 2 given event 1, I prefer this, is the number of outcomes favorable to the intersection of event 1 and 2 over the number of outcomes favorable to the event of 1 only. That is a mouthful, right? It warrants repeating. This read in English. The number of outcomes favorable to the intersection of event 1 and event 2 over the number of outcomes favorable to event 1 only. And this is read as the probability of event 2 given event 1. Okay, what we need to do, now that we have a formula handy, is pluck apart the sentence, right, so that we fill in E1 and E2 appropriately. Right. The trick that seems to work for the most part is look for the word given, as the old saying I, all right? And then what follows it is E1, or what you could sometimes call A if you prefer, all right? So I'm going to abbreviate higher than D, right, when I'm filling in E1 and E1 and E1 in these 3 places, right? What might be good is to say, all right, a grade greater than D. That seems like a fairly concise, intuitive way of writing it. So a grade greater than D. Perhaps there is a better way, more concise, succinct way to write that, but it hadn't occurred to me. Anyhow, so yeah, I'll do it here instead. Okay, now as far as E2 is concerned, it's the probability of getting an A, right? Just not to confuse A, the letter grade that a person can get, all right, instead of A in the formula, some other version of this, all right? This would be E2, all right? And I'll put this in sort of little quote marks, all right? A, all right. I'm gonna put this here as well. All right, we're basically good to go. Now to clarify what is going on here, all right, and just realize, just to complete this thought, this conforms to the alternative way, the alternative perspective of this. E2 is the most specific characteristic, and A is one out of potentially several choices that are greater than D. So it is the most specific way of talking about the the grade you get. Okay, so if I were to read this, right, again, I'll put this little thought cloud here, right? The number of outcomes favorable to the intersection of grades greater than D and a grade of A, right, over the number of outcomes favorable to grades greater than D only. That's what the denominator would be. Just for the sake of space. Let me draw a picture of the set, even though that is not asked, right? Because I think it will illustrate what numbers we're going to use. Here is sort of a side note here. Suppose these are the options for grades. A, logically. B, C, D, F, and let's perhaps say incomplete. All right. This is the total set, right? The sample space. Right? Simultaneously, you could write a set that are comprised of grades greater than D. The grades, as anyone knows in school, right, that are greater than D, and I'm not using negatives or positives, like a B minus or whatever, just the whole number of grades, if you will. Things that are grades greater than D would be A, B, and C. Right? So I would put that here. Okay. And then lastly, if you wanted to, you can have a third set, which would probably seem pretty silly, set of grades that are A. Well, there's only one grade in that case if it's a grade of A, and that is A. Nothing else. Anyhow, taking the time to basically illustrate that might help us decide what the numbers are here. So, without making it too sloppy, let's figure out what the denominator is first, because I think that's probably easier. We're just looking for the number of outcomes favorable to grades greater than D. Let's look at this set. How many grades greater than D are there? 1, 2, 3. So the denominator here is 3. If we're considering the number of outcomes favorable to the intersection of grades greater than D and A, right? The intersection would be the intersection of these two sets here, the set of 3 elements here and the set of 1 element here, and it would only be the things that they have in common, right? What is in both? This is what is in both. How many is that if we're looking for the number? 1. Right. That means that this is your probability. Probability is 1/3, which if you wrote it in the style of a percent would be 33 1/3%. given those two conditions. Last thing, I kind of had fun when I wrote it. I stole it, right, from your textbook, or what would be your textbook, but I changed the names because it made me happy. I was typing this late last night. What will be available to you is an example of having to take the information from a table, right, to answer one of these types of questions. So this will be available in Canvas, all right. A table that looks like this, and we can answer several questions. So let me walk you through this. And I may have to draw it, just not to have to keep doing this. Oh yeah, I'm telling you, we're good. Nah. Ferocious style, knocked over my freaking cards. Great. Alright. Pardon my French. Alright. Don't lose your cards, because they look making a mess here. Get more excited. The math. Throwing stuff around. Alright, I think that's good. I hope I haven't lost any cards. I don't really want to have to count these later. I think I might have to. Right. Well, put those back. Keep them out of trouble. Stay there. Alright. Okay, here's an example of conditional probability that you can answer given a table. The table will basically make answering the questions easier, right? As long as you know what to look for. Right? Here's as it is prepared. Results from a recent coffee taste test. Market research, you might say. And there'll be two brands, right, which this is the part where I amuse myself. Right, when you write word problems or something, right, and you take them maybe from some other resource unless you write them from scratch, all right, don't feel bad, you know, about taking a little artistic license with the labels, you know. If it makes it amusing to you, in theory, it will make it that much better for your students. Hopefully. Right? So, I chose two brands of coffee, whatever they came up with, I just changed the names. All right, and here's what I thought was amusing to me, because it's what I drink. Right? All right. I'll put it in blue. Chock full of beans. Beans. Not to infringe upon any copyright here, or to speak disrespectfully of the proprietary blend in question and its competitor, Big Bag of Nonsense, which I also like. Although it is more expensive. Okay. As the dollar sign. Ew. Okay. Now they were kind enough to put some totals here, and I really should fill in that as a label here. And these are the brands here. And then they surveyed women and men. See what they like. And then down here a little bit further, they also took some totals respectively. And this is the information that they have. For big bag of nonsense, right? Just because I'm home red. 75 women prefer big bag of nonsense coffee. For men, 40 people surveyed, 40 dudes, right, like big bag of nonsense. And that would make, naturally, if you added them, 115 people total. For a chock full of beans, beans. This is very bad English, don't imitate this, right? Women, 50 women surveyed like chock full of beans, and 60 men surveyed like chock full of beans, and that means 110 people total like that. Okay, now you can read this two different ways, right? The total number of people in general are 225. 110 people of this favor, and 110 and 115 of each brand of coffee is 225 people, naturally, right? Okay, if you wanted men total, right, then men is simply 100. And if you want women total, it would be what? 125. So, okay. Now we can answer these questions. All right. Question number 1. Right. If one of these individuals, I'm just reading what is written here. If one of these individuals is selected at random, determine the probability the individual selected prefers big bag of nonsense coffee. So basically, problem 1 is this question. The probability of a person that likes big bag of nonsense. And there's nothing fancy about that, right? If we wanted to dig up one of our old formulas, right, what would it be, right? It would be the number of people who like big bag of nonsense over the number of people in the sample space, right? Which is the total number of people, really. Right? What is the total number of people out of the entire survey? 225, right? What is the total number of people, because they're not specifying male or female, all right? But generally that like big bag of nonsense, 115, right? If you reduce this fraction, right, which would be ideal, you would get 23 out of 45. If you converted that to a percentage, you would get about 51%. Looks like more people, slightly more, perhaps like big bag of nonsense. Right? And the numbers would indicate that as well, right? There's more people total here. Okay. Let's see. Next question. The next question is the probability of, if a person is selected at random, what is the probability that they are a woman? And you might abbreviate it like so. The probability that the randomly selected person is a woman is equal to the number of women over the number of people total in the sample space. Right? So the number of people total is not going to change, it's still 225. All right? Versus the number of women total, you'd have to read this way, is 125. All right? If you reduce this fraction, you would get 5/9 ultimately. And then the percentage would be something like 56%. Right. Apparently there were more women surveyed, and again, the totals reflect that. There's 125 women involved here, there's only 100 men. Now as we get down to question 3, hope that's not too faint. Question 3, try this, is the probability of the individual selected prefers big bag of nonsense given that a man was selected. The way that you would abbreviate that is like this. The probability, and here, this will be the issue of which is E1 and which is E2. We need to decide that up front. All right, I'm going to point at this problem just to guide you along here. What's the probability that the person, the individual selected, prefers the big bag of nonsense coffee given that a man was selected? All right. Because it follows the word given, all right, let's assume that men are E1 in this case. All right, they're the less specific case. Whereas big bag of nonsense, that is E2. It's a more specific type of person. So in this formula, it's going to be big bag in place of E2 and men in place of E1. And the way that that would translate then is like so. The number of men intersecting big bag of nonsense over the number of men only. Okay. If we translate that, again, the denominators are probably easier to deal with. So what's the number of men total? Here's men, you're reading this way, 100 men. Put my thing before it falls. Okay. Okay. Now as for the intersection of men and that happen to like big bag of nonsense, right? The intersection of men that like big bag of nonsense, this is where the table becomes helpful. You could zero in on men that like big bag of nonsense. That's the intersection without having to draw a set. It's in the table. So it's 40. All right, and then you could pull tricks. All right, 40 out of 100 is already 4 over 10 or 2/5 if you like it in the style of a fraction. But more practical would be to convert it to a percentage. All right, if it's already over 100, it's already 40%. And it's exactly equal to that, as opposed to rounded at all. Problem 4, I'm jumping the gun here. 4, right? I should be a good guy and hold this up. All right, the probability that the random person selected prefers chock full of beans, right? Given that a woman was selected, right? Again, for the reason that this follows the word given, I would assume that women in this context are E1. So if this is my formula, E2 given E1 is equal to the number of E1 intersecting E2 over the number of E1. Here's how we would translate that. Women are less specific in this context, all right? Women that like chock full of beans, all right, are the more specific type of women. So chock would be E2, all right? W, chock, all right? And then it's just the number of women again down here. Sorry for the sloppiness, right? But we need to make sure that that is designated correctly because that would affect the fraction that we get as a probability ultimately. So again, I would start with the denominator because it's probably easier. What is the number of women total? All right. The number of women total are 125. Again, I don't want my thing to fall. Okay. Now, what is the intersection here? of women that happen to prefer chock full of beans, right? Again, the table comes in handy when you're trying to get that number because it is basically the coordinate, like if you're playing Battleship, you know, you read the ABC on one side and the 1, 2, 3 across. All right, it's like coordinates. Women who like chock full of beans, all right, 50. That is the intersection as a number. Okay. All right, and if you simplify this fraction, it gets down to 2/5 again. And then that is exactly equal to 40%. So the answer to problem 3 and problem 4 is coincidentally the same probability, but it's talking about two distinct things, two distinct scenarios of men who like, you know, big beta nonsense and women who like chock full of beans. Okay. Let's see. Move along here. Problem 5. Okay, now again, read this. This one is going to be a little tricky, so be careful. All right. The probability that the individual selected is a man, right? Given that the person prefers chock full of beans coffee, right? Notice that chock full of beans is following the word given in this case. So again, if I wanted a simple way to not worry about what is E1 and E2, I would look for the word given and then go whatever follows it is E1. So here's the formula. E2 given E1 is equal to the number of outcomes favorable to the intersection of E1 and E2 over the number of events favorable to E1, outcomes favorable to event 1, which is really the total of E1. Okay. All right, so since chock full of nonsense in this context is following the word given, then chock full of nonsense is what is going to be E1. So that means that you would put chock here and chock here. All right? And men would be E2. I guess you could think about it this way. Why are men E2 as well? All right. Men are a more specific characteristic in this context because they're men who are the chock full of nonsense people. Pardon me, chock full of beans. I can't even figure out my freaking nomenclature here. Men who prefer chock full of beans are a more specific type of man. All right. So anyhow, barring that again, look for the word given. This is what follows the word given, chock full of beans. Okay. So men would be here. Okay. Now when we're filling in the denominator here, let's look for total people who like chock full of beans. All right, 110. That's your denominator. The intersection of men who prefer chock full of beans. Let me back up a little bit. Why men are more specific? Because they're designating a gender to or sex, whatever. All right, to a customer. Right. Men are the more specific, are the specific customer of this brand of coffee. Right. Because what could they be? They could be women as well. Right? Okay. So the intersection of men and chock full of beans, right? 60. Right. The other half of that would be women naturally. Right? They're more specific. We're designating men as E2 in this context. Okay, so 60 out of 110 is the fraction simplified 6 over 11, which if you converted it to a decimal and then a percentage would be something like 55%. And now the last one. Okay. 6. 666. 66 signature. Okay. Here's the last question. All right. The probability that the individual selected is a woman, given that the person prefers big bag of nonsense coffee. Okay. And again, because big bag of nonsense follows the word given, I would assume then that big bag of nonsense in our formula is actually E1 in this context. It's because of the way that the sentence is formulated. Big bag, E1, which means when you're filling in the rest of this, it's going to be the intersection of big bag. And then for E2, women are the more specific customer, or the specified customer, because again, there's two types of customers, at least according to this table, males and females. So men and women. So W, big bag is also down here. Okay, so again, do the denominator because it's probably easier. What are the total number of big bag customers? 115. What is the intersection of big bag customers and women in general? 75. So if you simplify the fraction, 75 over 115, eventually you get it down to 15 over 23. And in terms of a percentage, that's about 65% for that. Okay? Okay. And I believe that is it. Let's see, let me just double check everything is okay. 55. Good. Alright, like I said, this is the only handout for today. You can print that if you are inclined to. And, as far as homework is concerned, naturally try, just for the sake of experience, section 11.6, right? And we're done, right? That is the end of the semester. So, as far as the final is concerned, right, I haven't checked my email today, but I think that nobody wants to make a decision about the final because they want me to have the freedom, which is very kind of them. So I'm going to make a final exam. I'm going to type it out so that you have basically a summary of the material. Right? That means that way, if you take the second semester of this class, which I want to say is MAT-113, and or you're taking the praxis examination, which is the real goal here, I'm going to just simply give it to you. Right? Now, as far as the grade is concerned, because of the conditions that we are living under, I have no way of collecting it. So I don't feel bad about making it because to me that's being very thorough. But here's what I'm going to do. I'm going to spend probably next Monday making your final exam. And then I'm going to simply give it to you to have it. Okay? All right. I'll talk to you via email. All right. Be careful. All right.